Hello, good day everyone. Welcome back to our class. As you can see here, we have wave motion for SHS and WASSCE. I'm just going to take my time through everything that is very important as far as wave motion is concerned so that we can be able to cope with our SHS education and our WASSCE exams. Please don't move away from us. Let's stick together and let's work together as a team. Good. Now, we are going to be starting with definition of a wave. Now, a wave is any disturbance in an elastic medium carrying energy from one point to another point through a medium without the medium as a whole moving. Without the medium as a whole moving. Now, let me just give example. Example is, let's say you have a house. I have a house here, and then I have another house here. Okay, and you want to send something to this house, but this time around you're sending the thing and you give it the object. Let's say you have an object here and you want to take it to this house. Okay, but you are walking through a certain distance to take the object, so you have to walk to the distance to take the object to this side. Okay, but wave motion is saying that no, I want to send this thing to this side. Okay, but I don't want to walk through to the side, but I would rather want a situation where this will appear here in terms of transferring from one point to the other. So in case of carrying energy from one point to another through a medium without the medium as a whole moving. Okay, now matter is made up of atoms. So if you want to talk about matter, matter is made up of what? Atoms. Okay, so every particle consists of these atoms. A quick example is the air around us. So if you want to take the air around us, it consists of these atoms. So let's say these are atoms around us. So you are standing at this point and another person is standing at this point. You are sending a message to your brother here. Once you speak, okay, what happens is that the atoms that are closer to you receive whatever you are spoken in terms of energy. Okay, and these atoms, they vibrate. Okay, once they receive energy, they get enough kinetic energy so that they can be able to vibrate. Okay, but they have, where they are now, we call it the rest position. Okay, that position is where they finally settle no matter what movements that they do. Okay, so even though they receive energy and they can be able to move to and fro, if we say to and fro, it means you are here, you go and come, but you have a rest position that you can finally settle. Okay, so the atoms that are closer to where you speak receive the energy. They move to and fro, and in their forward movement, they transfer the energy to the nearest atom. The nearest atom also receives the energy and is able to move to and fro, transferring to the nearest and transferring to the other nearest and transferring to a point where it gets to this point. Okay, so you realize that what you have spoken or the person sending the message, him or herself, is not moving, but the message is able to move to the person that we want to receive. Okay, and this is what we are talking about as far as wave motion is concerned. So we are saying that a wave is any disturbance in an elastic medium carrying energy from one point to another point through a medium without the medium as a whole moving. And this is a quick illustration of what is happening here. So we have a rest position and we have what we call restoring force. So restoring force is the force that when the object moves, it brings it back to its what? Resting position. A quick example of this is, I think I've talked about sound, so I can even add sound here. Okay, so we have radio waves, we have water waves, we have light waves, we have television or TV waves, and then we can have sound waves. Good. So these are all examples. There are several examples of waves which we can also find ourselves. Then at the type of waves, we have so many types of waves. Waves can be classified as a transverse wave. It can be classified as a longitudinal wave. It can be classified as a progressive wave. We can have a stationary wave. We can have a mechanical wave. And then we can have an electromagnetic wave. let us quickly move on to the first type of wave. Okay, so the first type of wave that we want to talk about is the transverse wave. The transverse wave. Now, the transverse wave is, now if a particle is disturbed, okay, if this is a particle and we are sending a wave across to a side, so this is A and this is the side B. Okay, now remember that these are the particles that are doing the transfer. Okay, so this is receiving before it sends to this, before it sends to this. So this is the direction of what? Motion. Okay, now for transverse waves, the direction of motion is at right angles to the disturbance. So the disturbance is here. So this is the disturbance, which are upward and downwards, and these are the directions of motion. So a transverse wave is a wave in which the disturbance is at right angles with the direction of what? Motion. So that is what a transverse wave is all about. Then a longitudinal wave. A longitudinal wave is a wave in which, so for longitudinal wave, if these are the direction of the wave, then the disturbance is also what? In the same direction. So the disturbance are parallel to the direction of movement of the wave. That is what we have for longitudinal wave and transverse wave. Let's move on to what we call the progressive and stationary waves. All right, so the progressive wave. Now, progressive wave is simply you have a point here, let's say A, and then you have a point here B, and you are transferring wave from A to B. Okay, so a transverse wave can be progressive, where we call it the transverse progressive wave. Okay, and a longitudinal wave can also be a progressive wave, where we can call it longitudinal progressive wave. So all what progressive wave needs is for energy to be transferred from one point to another point within a medium without the medium itself what's moving. So that is what progressive wave is all about. Now the next wave is a stationary wave. Now for stationary wave, let's say I have two waves. So stationary wave, I have two waves A and I have another wave B, and this is the wave motion for the first wave. Okay, and the second wave also starts from this point. Okay, good. Now for stationary wave, what is happening is that there are two waves of equal amplitude, in that it is going to meet another wave. So you have a positive plus a negative wave, and anytime you have a positive plus a negative, you realize that the net energy over there is what? Zero. Okay, so this means that on a whole the energy cannot flow, but is only located at certain points. Okay, so you can have energy located at certain points within a stationary wave, but they are not moving. Okay, then the next one is an electromagnetic wave, which we can talk about, or we'll talk about as we move on in our class. Let's quickly move on to something else and then see what's going on. All right, people, let's move on to what we call the basic quantities of wave. Basic quantities of wave. Now, the first one that I want to talk about is what we call the amplitude, represented by capital A. Now, if you look at the diagram here, I have a diagram of displacement, or a waveform for the wave motion, displacement against time in seconds. So displacement in meters against time in what? Seconds. Now this line here is representing the rest position, or the equilibrium what? Position. So that if this is our 0 point and an object starts to move from this, it goes and then comes back this way. So this is the positive aspect and this is the negative aspect. Okay. Now, the maximum displacement is the highest point that an object can get to. So here, this point is the highest point that the object can get to, and that is what we call A, which is the amplitude. So the amplitude is the maximum displacement of an object from its mean position. So maximum displacement from its mean what? Position. So the maximum displacement of an object from its mean position is what we call the amplitude. The next thing that I want us to talk about is what we call the wavelength with a symbol lambda. The wavelength is defined as the distance moved in one complete cycle. So the wavelength is the distance moved in one complete cycle. As I said earlier on, you move from here and go here. This is half of a cycle, and this is half of another cycle. So the distance from here to here, we can call it the wavelength. Or if I want to start my cycle from here, then this is half cycle, this is another half cycle. So the distance from here to here can also be the wavelength. If I start from this point, then this is quarter of a cycle, this is half of a cycle, this is another quarter of a cycle. So I can say the distance from here to here is what? Wavelength. So it depends on the diagram that will be given to you and how you are going to find what? Your wavelength. So it is the distance for one complete cycle of oscillation. And then frequency. The next thing is frequency. And please, the wavelength is measured in meters. The amplitude is also measured in what? Meters. Then the next thing that I want to talk about is what? The frequency. The frequency is the number of complete cycles in a time of what? 1 second. So the frequency f, small f, is number of cycles. So assuming it is going here, this is 1 cycle, this is 2 cycles. So all the number of cycles that we can have in a time of 1 second is what we call the frequency. And then the period t is the time taken to complete one full cycle of oscillation. So from here to here up to here. So if this is 0, this is 1, this is 2, this is 3, this is 4. Then from here we can say that 0, 1, 2, 3, 4, where 4 is the time for one complete cycle, and the unit is seconds. So we can say that the period t is what? 4 seconds. Okay, good. Now the next thing that I want us to talk about is the phase. Is what? The phase. Good. Now the phase is the position of a particle at any time or at a given time on the curve. So let's assume that I have a particle here A, and I have another particle at this point. Let's call it B. I have another particle at point C. I have another particle at point D. If I look at A is the beginning of a cycle, and then this B is the end of a half cycle. So this and this, I can say they are out of phase. Okay, so 2 points can be in phase, or 2 points can be out of phase. So if I'm talking about out of phase, then A and B are out of phase, but A and C are in phase. So in phase, we can say that A and C are in phase because A is moving or starting, and then C is also what? Starting. But B and D are also in phase. But if I take A and B, they are out of phase. B and C, they are out of phase. C and D are also what? Out of what? Phase. Okay, good. Now the next thing that I want to talk about is what? Velocity. Please again, look for the definitions of all these so that you can learn how to write the definitions, because you can be asked in your what? Exams. Good. The next thing that I want to talk about is velocity. We know that velocity is equal to displacement all over what? Time. Okay, so I'm still using my curve again so that we can use the curve to derive the equation that we want to derive as far as velocity is concerned. Right now, if you look at this diagram, you will see that the displacement is the maximum displacement here, which is the amplitude. Okay, so if you look at the diagram, you realize that this is our amplitude A, and the distance from here to here is our what? Wavelength lambda. Okay, so if the particle starts from here, this is its maximum displacement, and then this is the distance. And at that point, that is also our period what? T, which is the time for one complete cycle. So the velocity is the displacement over time, which is the distance that the particle has gone to obey all over the period what? T. Okay, but we know that T is equal to 1 over F. So we can say that velocity is equal to F multiplying what? Lambda. Okay, so this is the relation that we have for velocity, frequency, and then wavelength. And then this is also a relation that we have for velocity, wavelength, and then the period. And the unit remains meters per second. The unit for period is second, and the unit for frequency is per second, or the hertz per second, or the occurs, which is sometimes h z. Okay, good. Now let us move on to write some other equations. Okay, so on the board here we have velocity of waves. Velocity of waves. There are so many equations for velocity of waves. The first one is velocity of wave in a straight string, where is equal to square root of the tension over mu. T here is representing tension. This is mu, which is mass over length, or mass per unit what length. Okay. Then velocity in solid, where is equal to square root of E over rho. Rho is density. E is the Box modulus, which is a constant, and will be given to you in a question. In a liquid, we have V is equal to square root of K over rho. Rho is the density. K is called the Young's modulus, which is also a constant. Then velocity in an electromagnetic wave, V is equal to 1 over square root of mu epsilon. Now, the mu here is permeability of the medium, which will be given to you, and epsilon is permittivity of the medium. These are all constants which are going to be given to you. We can also have velocity in a gas. This is a little assignment that I want you to do for yourself. Okay, good. Now the next thing that I want us to move on is what we call the general wave equation. The general wave equation. That is what I want us to talk about. The general wave equation. Now the general wave equation, we are saying that for a wave, y is equal to a sine into bracket omega t plus an angle theta. Y is equal to into bracket a sine omega t plus an angle theta, which is representing our general wave equation. Okay, so let us try and do a little expansion as far as our equation is concerned. Good. Now, omega, from the diagram here, this is the amplitude, this is the angular frequency, angular velocity, this is time, this is the initial phase angle. Okay, and this whole thing is a phase angle. Good. Now we can, omega is equal to 2 pi f, where f is frequency. Okay, so this whole setup can change. And then also the theta is equal to kx. Okay, theta is equal to kx, and then k is equal to 2 pi all over what? Lambda. So it implies that theta can be equal to 2 pi x all over lambda. So if I have this, and I have this, and I have this, let me just rewrite the equation again. So the equation can be written as y is equal to a sine 2 pi ft plus, let me just bring plus or minus 2 pi x all over lambda. Sometimes it is plus or minus. The plus or minus determines or depends on the direction in which the wave is moving. Or when you are given a question, sometimes it is given to you as positive or sometimes negative. Okay, let us now go ahead and define the terms in the equation. Now from the equation, you see that we have our A. We know our A already to be amplitude, so we have y is equal to a sine into bracket 2 pi ft. The f there is what? Our frequency, and then our t is our time. Then we have 2 pi x all over lambda. The lambda there is what? Our wavelength. The lambda there is our wavelength. And then what haven't we defined? We have not defined our k. Our k is our spring constant. Our spring constant. Or since we are dealing with waves, then it is what we call our wave constant. So our wave constant is equal to what? K. And x is the distance that the wave has covered at a certain point in time. Okay, let us continue with what we can add to the equation. Okay, so the equation has been rewritten on the board here. We have y is equal to a sine 2 pi this. Now we know that f is equal to 1 over t, right? So we can still rewrite our equation. And also, we know that v is equal to f lambda. Okay, so we can manipulate this equation in so many ways to fix in t or to fix in velocity. Okay, even from this equation, we can say that y is equal to a sine, since there's 2 pi and there's 2 pi here, I can bring 2 pi out and then open bracket ft. And since f is also 1 over t, I can make it small t over capital T here, plus or minus x all over lambda. So the equation can also be written in this way. This equation can be written in a lot of ways, okay? So let us just take note of the definitions that we have done and let's apply. Let's see how we are going to apply. Now, if you are given a question, you know that the question in this waveform will always be given in a waveform, and you are going to compare to the general wave equation. You are going to do what? Compare to the general wave equation. So let us quickly move to some questions and then see what we can do as far as our class is concerned. Okay, now let us continue our class with a question that we have on the board. Okay, I'm leaving this equation, and this is another equation for wave number. If anytime you are asked to calculate for wave number, it is 1 all over the wavelength. That is how you calculate for the wave number. Then we have what we call the phase difference, which is this symbol is k multiplying change in s. Change in s can be x2 minus x1, which is the path difference. So if an object starts from a certain point and ends here, so if this is, let's say, 2 meters and this is 5 meters, then change in s is equal to 5 minus 2, and then you multiply by the constant k. Okay, given that y is equal to 10 sine 40 pi t minus 8 pi x, calculate the following. Okay, so first thing in your solution, you write the question y is equal to 10 sine into bracket 40 pi t minus 8 pi x. This is equation 1. Then from the general wave equation, so you come and write the general wave equation. Okay, so from the general wave equation, we know that y is equal to a sine into bracket 2 pi ft plus or minus 2 pi x all over what? Lambda. Let's call this equation 2. But since this is minus, then we have to make this one also what? Minus. Okay, so this is what we have as far as the general wave equation. Let me just move the camera slightly so that we can get everything here. Good. So these are our two equations. Good. So the next thing that we want to do is to compare. The next thing that we want to do is to compare. So let us quickly compare equation 1 and equation 2. So from here, we can say that a is equal to 10. Let us call this equation 3. So comparing equation 1 and what? 2. Comparing equation 1. So this is a, this is a. Then we can say that 40, or okay, so we can say that 2 pi ft is also equal to 40 pi t. This is our equation 4. Okay, then we can say that 2 pi x over lambda is also equal to 8 pi x. Let's call this equation 5. So now that we have done all the comparison, let's go to our first question, amplitude. So A. So from equation 3, we know that A is equal to 10, which is in what? Meters. Okay. Then B, we have to find frequency. So we look for the equation where there is frequency. We can see that from equation 4, 2 pi ft is equal to 40 pi t. Pi t will take pi t, then f becomes 40 over 2, which is equal to 20 hertz. That becomes our what? Our frequency. The third one is the wavelength. The wavelength is, so you look for an equation that has wavelength, you say it. So from equation 5, we can say that 2 pi x over lambda is equal to 8 pi x. Okay, so pi x will take pi x away, so that lambda becomes 8 over 2. So lambda becomes 4, and it's what? Meters. Okay, then the d aspect, the v is equal to f lambda. We have to calculate for the velocity. So the velocity v becomes equal to f. Where is f? F is 20, our lambda is 4. So this will give us 80 meters per second. This is how we calculate for what has been given to us. So you have to know that all the time you are what? You are comparing. All the time you are comparing. And once you are able to do your comparison well, you shouldn't struggle with the answer that you're getting. Okay. Okay, so I think there is something that I have to do here. Look here. This one is supposed to be 1 over 4. It's supposed to be 1 over 4 rather. So you're going to get 0.25 meters. Yeah, 0.25 meters. Implying that here you have 1 over 4. So you have 20 divided by 4. That becomes the velocity, which is equal to 20 divided by 4. And once you have 20 divided by 4, you know this goes into a 5, so you have 5 meters per second. Okay, so one thing that we have to make sure we avoid is this placement values, or how to move from up to down, so that we don't make mistakes. Okay, thank you very much. Let us try one last question and then see how everything goes. Okay, people, so let's look at the question on the board. Our last question here. An electromagnetic wave travels through kerosene. Okay, so we have an electromagnetic wave which is traveling through kerosene with a velocity of 2.4 times 10 to the 7 meters per second. If the permittivity of kerosene is 6.77 times 10 to the negative 12 farad per meter, find its permeability. Beautiful. Now, this is a question of recollection. You have to recollect. So first, let's write what has been given to you. So V of the kerosene is equal to 2.4 times 10 to the power 7 meters per second. Then we have been given the permittivity, which is epsilon, 6.77 times 10 to the power negative 12 farad per meter. You have to find the mu, which is unknown. Now, if we can recollect, we know that our velocity v is equal to 1 over square root of mu epsilon. If you remember this equation, so let's square. So v squared becomes equal to 1 squared all over mu epsilon this way. So if you want mu, then mu will go up, then it becomes 1 all over v squared multiplying epsilon. Okay, so let's move on to this side. So mu becomes equal to 1 all over 2.4 times 10 to the power 7 all squared multiplying epsilon, which is 6.77 times 10 to the power negative 12. This is what you have to do. If we use our calculator very well, then we are going to arrive at 2.026. We arrive at 2.026 times 10 raised to the power negative 4 times 10 raised to the power negative 4, and the unit is Henry per meter. This is the value that we are getting for our mu. Ladies and gentlemen, thanks so much for enjoying our class and being part of our class. Hopefully, we are going to take part or take you back to a lot of things to keep on making you understand what we are doing here. Kindly subscribe to our channel. This is the longest video that I have made since I started my class, and I hope this is very helpful. I've tried as much as possible to fuse everything that has gotten to do with wave motion as far as our WASSCE is concerned. If you have any problem, you can have a comment, or comment if there is anything that you need. Just comment and give any question that you want to give to us so that we can solve for you. Thank you very much. Kindly subscribe to my channel. There is more and more coming. Thank you. Have a nice day.